Hello, everyone. I'm Habiba from Purdue University, and today I'll be talking about our work on inferring semantic location from spatial maps in mixed reality devices. Now, we had a little bit of background in the earlier talk, but just to cover all bases again, the influx of reality-altering headsets and applications have brought mixed reality into the limelight over the recent years. The mobile industry has been striving really hard to enable more comfortable and realistic MR experiences for users. All major mobile industry stakeholders like Google, Microsoft, Apple have now their own MR development frameworks, not just for traditional mobile devices like smartphones and tablets, but also for dedicated headsets like HoloLens and MetaQuest. Now, these mixed reality devices integrate virtual content into the user's physical environment and allow them to interact with both the real and virtual content at the same time. This not only enables applications in entertainment and gaming, but also provides interactive healthcare, education, and e-commerce experiences to the users. Now, in order to enable all these different applications, mixed reality devices need to accurately locate themselves in the user's physical environment and understand the objects and surfaces present in the environment to seamlessly superimpose digital content into the user's surroundings. In order to achieve this, commonly available mixed reality devices, both dedicated headsets and off-the-shelf smartphones, are equipped with depth sensors like time-of-flight sensor or LiDAR sensors to capture a detailed 3D representation of the user's environment. This 3D representation is then used by mixed reality apps to overlay virtual content into the user's surroundings. Now, MR devices provide this 3D representation of the user environments to MR applications as a 3D spatial map. The 3D spatial map is basically represented by a set of 3D points, where each point is a vector of 3D coordinates in the space that represents the distance between the device and the points in the real environment. Now, on top of just helping mixed reality devices localize themselves in the user's environment, these spatial maps enable useful functionality for MR applications, like helping them place virtual objects in user surrounding, like a virtual pet on your desk, or detecting various obstacles and surfaces, and helping navigate virtual content through the user surrounding. So, since these 3D spatial maps are essential for enabling several different MR functionalities, all MR apps by default have access to these spatial maps without requiring any explicit permission from the users. And access to these 3D spatial maps of the user's environment poses serious security and privacy concerns, as these maps embed privacy-sensitive cues about the user's environment. For instance, a spatial map captures detailed characteristics of the environment, such as its geometric properties, like the length and width of the room, or the type of objects that are present in the environment, like a TV or a kitchen sink, and so on, which can help infer private information about the user. So in this work, we show that similar to how humans perceive an indoor environment based on its layout, object, and surface properties, an adversary can extract these characteristics from the 3D spatial map to infer the user's location, that is, the type of indoor environment that the user is present in while using this app. We refer to this indoor location as the semantic location of the user and build LocIn to demonstrate this attack. Now, in order to launch the LocIn attack, we assume that the adversary has access to an MR application on the mixed reality device. We assume that the adversary does not have any information about the target user's environment and trains the attack solely based on publicly available spatial maps datasets. We also assume that the malicious app used by the adversary does not require any explicit permission, like location, except having access to the camera, which by default most MR applications need to enable mixed reality content. We also assume that the adversary only leverages the 3D point cloud of the spatial embedded in the spatial map without any additional information like color or normal vector to generalize this attack to various mixed reality devices. Now, on top of just inferring a user's indoor location, this attack has serious security and privacy implications. For instance, an attacker can combine the location information inferred from the spatial map with other information about the user to launch physical attacks like robbery and assault. Moreover, an adversary can gain a more fine-grained understanding of the user's routines, such as when a user wakes up, goes to work, just based on the inferred locations across time. This information can then be leveraged to deliver targeted ads and personalized ads and create detailed user profiles that can then be sold to data brokers and third parties for revenue. An adversary could even go beyond and combine the object and semantic information embedded in spatial maps with the inferred location to reveal additional private information about the user, such as their socioeconomic status, their accessibility requirements, their product preferences, as well as their identity and behaviors. So now that we understand that spatial maps have severe security and privacy consequences, it's important to mention that launching such location inference attacks in practice involves several different challenges. First, an adversary must be able to infer the target user's environment without making any assumptions or prior information about them. So given a 3D spatial map, intuitively an adversary could train a classifier that extracts high-level features such as structural and geometric properties through object detection and semantic segmentation on the spatial map. However, this is challenging as indoor environments of a given type typically vary significantly in their structural and geometric properties. For instance, two bedrooms in a home may be of different sizes and have different objects. Moreover, unlike image pixel arrays, a 3D spatial map is an unordered collection of points with non-uniform point density, which makes detecting objects and performing 3D semantic segmentation much more challenging. Lastly, spatial maps captured by mixed reality devices change dynamically in size and viewing angle when a user interacts with different MR apps. For instance, the spatial map captured of an environment while playing a game may be very different from the map captured while using e-commerce application. So based on these challenges and observations, we present LocIn, a novel location inference attack for mobile mixed reality devices, which exploits the 3D spatial maps to infer a user's indoor location. On a high level, LocIn begins by first pre-processing the input map by removing any outlier points and sampling the 3D points in the spatial map to a specific number of points to tackle varying app usage and generalize to various MR devices. It then extracts the geometric and semantic properties of the user's environment by extending a hierarchical neural network encoder, which generates a spatial feature representation of the user's environment. This representation is then fed onto LocIn's location decoder, which consists of three main components. The first component is a location decoder, which is a fully connected neural network that is trained to predict the type of environment solely based on the spatial feature representation. The second component is an object decoder that performs 3D object detection using the spatial feature representation to identify the bounding boxes for any objects present in the user's environment and assign labels to them. Lastly, the semantic decoder performs a fine-grained understanding of the type of objects and surfaces present in the environment by generating point-wise semantic labels for each point in the spatial map. Now, let's dive into a little bit more detail of LocIn's architecture. To learn the spatial feature representation of a user's environment, instead of relying on handcrafted geometric and semantic features, we leverage a deep neural network architecture for learning point-wise features. While LocIn's approach is not limited to a specific network, we extend a PointNet++ based encoder, which extracts hierarchical features from the spatial map that preserve spatial localities in the spatial map at different contextual scales. This allows us to capture spatial features even with varying map sizes and viewing angles. Now, given the user's environment spatial representation, LocIn predicts the indoor location by first extracting high-level geometric features and then combining these geometric features with the map's contextual patterns that are extracted through object and semantic segmentation tasks. Specifically, we leverage a voting-based module for identifying 3D points belonging to objects and a hierarchical feature propagation technique to detect surface and point-wise object labels for each object and surface present in the environment. We incorporate this contextual information into our learning representation for location decoding by using a multitask learning approach and training an end-to-end encoder-decoder architecture with an optimization function that leverages the loss functions for the location classification, the object detection, and semantic segmentation tasks. So using this learning representation, we are able to train a model that can classify the location of a given spatial map while simultaneously learning the contextual patterns that uniquely characterize the user space. Now let's take a look at LocIn's evaluation. So to evaluate LocIn, we used 3 data sets of spatial maps that are captured through 3 different mixed reality devices. 2 of these data sets are publicly available data sets captured by iPad with a depth sensor and a LiDAR scanner. We also collected our own data set of spatial maps through a HoloLens 2 device to just test the generalizability of the attack on different mixed reality devices. I note here that we trained the attack model on the 2 publicly available data sets using their training and test data sets, and we ensure that the type of environments in each set are distinct to ensure that the lock-in results are independent of users and prior knowledge about their environments. Here, now I'm going to show you about the lock-in's overall effectiveness in terms of its accuracy, precision, and recall rate in detecting the indoor location. As you can see, LocIn detects location with more than 81% accuracy on all 3 data sets without any prior knowledge or assumption about the environment. We also test LocIn's robustness against spatial maps with varying map size and find that even with the spatial map covering just less than half of a user's environment, LocIn can still infer the location with more than 70% accuracy. We also test the relationship between the number of points in the spatial map and the attack accuracy and find that the result accuracy improves as the number of points in the spatial map increases. So through LocIn, we make a step towards understanding the security and privacy risks associated with spatial maps on mixed reality devices. In our work, we also explored countermeasures against this attack. Of course, an immediate solution is to just limit the spatial map access to mixed reality applications. However, this is not feasible since they have important utility for mixed reality applications. We also investigated adding carefully designed noise to the spatial map to avoid leaking any sensitive information. However, such noise also reduces the accuracy for legitimate applications. So going forward, we will be looking into investigating countermeasures that keep the privacy utility trade-off in mind and also explore users' perception of the risk associated with such spatial maps. To find out more details about our work, please check out our paper or find me during the conference. And that's all I have. Thank you. If you have any questions, I'd be happy to take them.